All right, so today's date is 5/13. I'm going to be doing this together. It's going to be pretty self-explanatory. Just make sure everything is completed in your notebook for Newton's first law of motion, which is pretty much just the law of inertia. So an object of motion wants to stay in motion, an object at rest wants to stay at rest. So up here in this top box, we're going to look right up at this top box only. Let me go ahead and get my black pen out if I can find one. So inertia, what you're going to write in here, well, what is inertia? So looking up here, inertia, and I always spell this word wrong. Inertia is the resistance. Okay, inertia is the resistance of change. Inertia is the resistance of change in motion. So an object in motion really wants to stay in motion. An object at rest really wants to stay at rest. So inertia is the resistance of change in motion, comma, including changes to speed, direction, or state of rest. Okay, so that is what you're going to put there, and a couple of the key words that I'm going to underline. If you don't have an under or a highlighter, just underline them or box them or something. But inertia, our key word here being inertia, is the resistance, another key word, to a change. So resistance pretty much to change or of change, either in speed, direction, or state of rest. Okay, so that's all you need to put for that little box up there. And even though I'm going to be moving the paper over, we're going to put a little lobster there and a crab. So there'll be, oh, that looks weird. Oh, that looks weird too. Okay, so there we go. So just in case you can see it. So looking down here at these boxes, and we have kind of a little ball going down the ramp. This is, so the force is pushing this way. So here is our force. I'm just going to indicate that with the letter F. And this is the force causes the ball to roll down the ramp. Okay, so if I'm looking at this, my force, which is up here, so here is my force. Okay, the force causes the ball to roll down the ramp. Okay, so it could be a push, it could be the wind for all we know, but that is what is going to cause the ball to roll down the ramp. Okay, so looking at the second one, okay, we still have another force. We still have our force here. Again, identify that with the letter F. I'm just going to highlight it just so you're like, oh my gosh, yes, I know. So if the ball is being pushed upwards, trying to move upward, I guess I should have put an arrow showing these go down. But the upwards arrow, so there's a force, maybe it's wind, maybe it's a really strong person trying to push it, but there's opposing forces in this case because you're going uphill. So friction, okay, so that kind of invisible force, and gravity acts against, I don't know why I capitalize that, against the force on the ball, which is obviously why the ball does not roll uphill nearly as fast as, let's say these are equal forces. The ball is going to accelerate much faster going down the ramp than it is up to it because there's not a force against it. Friction, gravity are not working against it. Gravity is actually going to be helping it. All right, and then the last one. We have another little force. Here's our other force. This is our third force, again, identified with the letter F. So we have our little arrows moving along. So this is just a ball rolling down the, let's say, a frictionless surface, so which is pretty, good luck finding that. On a frictionless, that there was a ball rolling down this infinite hallway there was no friction or air resistance or anything else, the ball would just keep rolling because the object of motion wants to stay in motion. The ball, so on a frictionless surface, the ball will never stop moving. You're assuming this is kind of, there's no air resistance or anything else like that. Okay, ta-da, there we go. We got that part filled in. So let's look at these little arrows up here along the top. And we'll change it up with the different colors. So what is it pretty much in a nutshell? So an object in motion remains in motion. And just something you guys should be pretty much aware of. So if an object is in motion, it wants to stay in motion, which is why if you're in a car and the car all of a sudden comes to a stop, your body continues moving forward because an object in motion wants to stay in motion. Look at this aquatic theme I got going on. So an object in motion remains in motion with, so we're still continuing on, with the same speed and direction. Okay, so that frictionless surface, we're assuming there's no change in speed or direction, with the same speed and direction. So an object in motion remains in motion with the same speed and direction. So there's no reason it's going to change direction. Throw in a little Sharpie. Third box right here, continuing on. Unless acted upon by an unbalanced force. Okay, so unless it's acted upon by an unbalanced force, that object is just going to stay the same speed, same direction, unless there's some sort of unbalanced force. Okay, almost done with this one. All right, let me put, do I have any more aquatic animals? Oh, look at this, I got a sailfish. Cool. So I'm going to put him on there. All right, so looking at this little pendulum here. So what all does this pendulum do? I'll switch up the colors a little bit. Whoops. Oh, I almost dropped it. So this is the pendulum, just going to move back and forth, back and forth. So you can kind of imagine, Here it is again. There's all these different kind of levels of it. All right, so I added a little bit more to it. So a pendulum, weird word. A pendulum swings, if you're thinking about gravity and everything else, due to an outside force acting on it. Okay? So that's the only reason that it's going to roll, or not roll, excuse me, move, is because of that little pendulum. Any more aquatics? Okay, we'll just throw in a frog here. He's kind of big. Now looking at, actually we'll do the little roller coaster thing first. So looking at our little roller coaster, oh my gosh, I have one that's uncovered. Oh, there we go, thank goodness for crabs. So here's our little car, and our car is at rest. Okay, as the little roller coaster goes down. Here, oh gosh, time for our Miss Penny drawing. There's my little people. Oh, that's awful. Inertia. So an object in motion wants to keep moving. Inertia keeps the car moving. Okay, so we're still cruising along here. All right, so inertia keeps the car moving. Do I have any more aquatics? Oh, look, we have a, well, no, that looks like a turtle, not a tortoise, or tortoise, not turtle. All right, so we have it continuing to go up. Here's why. So we have our little car again. Oh my gosh, they're so excited. This person just Ralphed because he's like, oh my gosh, you just missed the Ralphing. Oh, he just threw up. But gravity, so at this point, what's pulling it down is gravity is a force pulling down. Okay, and so that's why the little car is constantly going. And then we'll just draw it again. Oh man, that one sucked. Okay, apparently we went from a 2-seater to a 1-seater. Oh well. All right, and it's just going to keep going. This last box. Okay, this last box is essentially just going to be answering a question. Do I have any more aquatic life? Lizard. Just stupid lizard. Okay, we'll put Monsieur Walrus right there. Gosh, we got a whole party going on over here. So the last thing we're going to do is, let me flip you over real quick. Explain what would happen to motion if friction did not exist. Okay, if you can't see it, I did just say it as well, so hopefully you can figure that out. So explain what would happen to motion, so motion if friction did not exist. Let me use blue again. And just write a complete sentence, relatively easy, this is the last part. If friction did not exist, just restate the question. Then objects in motion would never stop moving. Period. Okay, that's all I gotta put. Ta-da! Look at that. Oh my gosh. So there you go.